But what is the self? The self is a relation that relates itself to itself, or is the relations relating itself to itself in the relation. So the 1940s mathematicians, namely Samuel Eilenberg and Saunders MacLean, were developing algebraic topology, specifically certain things related to homotopy, when they eventually created the very general formal branch of mathematics known as category theory. Now, each category describes the structure and properties of basically a class of objects, and there are numerous examples which we can give. For instance, groups, rings, fields, sets, topology, etc. And the list truly goes on. There are just several examples of categories. It's a very interesting branch of mathematics. However, there are certain requirements for a class to be a category, and that is, first of all, an identity, meaning the existence of some kind of identitymorphism, which is really just any function such that it sends an object to itself within this category. So the identitymorphism here. And we have, more generally, a morphism, which is from any object to any other of the same object, basically. So it's to another object in the same category, and it's some sort of mapping or representation. And we'll get to see some examples later, but this is just the theory behind it. And we should be able to compose these different morphisms if we apply them sequentially. So we have this general idea of a morphism of any object within this category to another kind of object, to another object of the same kind. Now, furthermore, more generally, we have this thing called a functor. A functor is basically a mapping from one whole category to another entire category, right? And according to this professor, Paul Garrett, of the University of Minnesota, virtually everything fits into the idea of category, morphism, and functor. So that's very interesting. We get to see this very formal, general branch of mathematics, which most people don't really know about, but it really ends up being kind of simple if you do the research and ask questions, to take the initiative, And this is just simply part one of a presentation I'd like to give, just a brief bit of a presentation on some general mathematical ideas. So I say some random abstract maths with all logarithms equal. And so we have categories, we have functions, different kinds of functions, that is. We also have commutators, which we'll get to later, and these more specific kinds of groups. And so here we're about to start part two now, and I'd just like to mention that in certain contexts, category theory is actually used to introduce group theory. And so this is what we're getting into here. And that's sometimes category is used as an introduction, partly because there are just so many relationships amongst the groups and from any given group to other mathematical structures. So we have a bunch of these different relationships, which are actually called group homomorphisms, as we see right here, and there are different kinds of homomorphisms for groups. And I'll describe all of this later in the video. But first, I'd like to discuss really how a group is constructed, so to speak. How a group, what are the actual fundamental axioms, or properties that define a group, right? I list them right here. There are 4 main axioms, and they are, I'm gonna describe each one. Closure, for instance, that just basically signifies that each group is closed. That's a phrase that is typically used. And so if we have A, that's part of our group, capital G, and B, that's another element in the group, then basically, given an operation that kind of defines the group, we need to make sure that, let's say the operation is denoted by plus or something like that. We can even take it to mean addition in some examples. Not always, but that's just one example. So we basically know that A plus B is also a member of the group. That's, by definition, what must be true. So a group is a kind of structure, a kind of... you can think of it as a kind of a set, but it's a bit more than that. It's a more specific kind. It's really a set with an operation that satisfies these 4 axioms, right? So closure, we know that A mark B, or A plus B, A times B, whatever the operation is also a member of this group, of this structure, of this set, as long as A and B are also members, which is pretty intuitive. Associativity, that's another common one. You can see an image of it. Basically, if we have an expression that is A times the quantity B times C, then we need to ensure that that equals the quantity A times B times C. So that's all that means. You probably actually remember what that is from some kind of primary school. In many cases, they want students to know that that kind of property of the integers. That addition and multiplication are usually defined to be associative operations, actually. So that's a relatively basic idea. We also have identity. So there's some kind of most basic kind of building block, or I shouldn't say building block necessarily, because that could be confused with a generator, a group generator, which we'll get to later. But identity is kind of the most basic element of the group. So for instance, if we have the set of integers, all positive and negative integers, let's say they are closed. We're choosing the operation of addition. It's a very common example of a group, actually, because they're all closed under addition. If we have any integer plus any other integer, we're bound to end up with an integer. It's pretty intuitive. And I just said they are associative. Now, the identity for that case is basically to ensure that we take any element of the group, doesn't matter which one, and we add, or, perform the operation with the identity element, then we must end up with that original starting element, which doesn't have to be the identity. So the identity, let's call it E, or scripted E, or something like that. Let's ensure that A plus scripted E is equal to scripted E plus A is equal to A, basically. So it doesn't change the value of A at all. It just gives us what we started with. That's what an identity really is. And so if we consider the integers closed under addition, then for this identity, I'm sure you're already imagining this, I'm sure you've already pieced together, it would have to be equal to 0, really. It's our 0 element. That's what the identity really is. Now, in many cases, like in some other cases, for instance, if we wanted to take the set of rational numbers or something like that, and we want to choose it to be closed under multiplication, which does make sense. I mean, if we take a rational number and another rational number, multiply them, we're pretty much bound to end up with another rational number. So they're closed. Well, the identity we could choose for that one, well, actually, the identity we would have to choose under that operation would actually have to be 1. Now, in that particular case, we're multiplying by 1 to keep the same element. So that's the idea behind that. Now, also, we have another thing called inverses, which might already be clear to you. Let's say we had the group, as I mentioned originally, the set of integers closed under addition, and we want to take the inverse of 5, well, we pretty much know that using addition, the inverse would simply be negative 5. But speaking more generally, more formally in mathematics, we want to say that basically for each element of the group, we want there to exist, so it's like an existential quantifier. We ensure that there exists another element in the same group such that the first element plus its inverse, or times its inverse, etc., is equal to the identity element. So we're just kind of counteracting it in order to get to the identity under this operation, whichever one we choose. So this is just a very general idea, a group, and it's actually pretty intuitive, pretty easy to understand if it's presented right. So I hope I've done a good job. If you have any questions, just let me know. And as I mentioned earlier, we have group homomorphisms. It's just a very important aspect of group theory that basically sends one group to another through some kind of mapping or function. And we're going to get to that later. We're going to actually see some examples. It's really fun, really interesting, actually. Excuse me, it really is actually fun. And there are indeed more specific kinds of groups as well, such as abelian groups. It's a very common one you'll hear, and that simply means that commutativity is also satisfied by this group with this predefined operation. So basically we have associativity here. You may also be familiar with commutativity, where basically a plus b is equal to b plus a. That's, the simplest example of commutativity. And that's also, many students learn that in school as well. But it's just having that added requirement of commutativity for all elements. And that's what makes the group abelian, excuse me. It's a very common word you'll hear in mathematical discourse. It's an abelian group. Oh, interesting. That's one of those fun ones where we can get commutativity involved. So I'm sure it's rather obvious that the set of integers with that operation of addition is clearly an abelian group. For instance, 5 plus 3 is equal to 3 plus 5. And that works for every element, obviously. I was just giving an example. We would get 8 either way. We also have finitely generated groups. Basically, a group generated by a finite number of elements. And we'll actually have to explain that later. There are also groups that exist on elliptic curves. So now we're sort of getting into algebraic geometry a bit. But it turns out that we can create, quote-unquote, we can consider a group to exist on a curve, actually. And we can consider the points of that curve as long as those points are described by numbers in some kind of particular set, which we've defined, which we've specified. We can consider all those points to be basically elements in our group. And that gets very, very interesting. I'll put some citations in the description for you to research more about that, actually. Because that's very useful in modern mathematics, and also very interesting just from a pure mathematical perspective. So the groups that exist on elliptic curves, they're truly very interesting. And it cannot be exaggerated. Now, we also have groups of polynomial roots. Now, that's basically the idea behind Galois theory, actually. But it's very interesting. If we take the roots of polynomials, consider the set that they form, and we can consider different kinds of permutations of those roots, and then of those permutations, they can form a group. So that's a bit abstract for me to just declare that and say that right off the bat, but I'm just listing different kinds of groups that you see in mathematics, which you might not think of originally. But we also have something called a Lie group. Now, this is getting to the more difficult side. This is actually kind of going in increasing difficulty of what I'm describing, but it's still nonetheless very fun. We have Lie groups. You can see Sophus Lie right here as a picture. And they're kind of a combination of group theory and calculus, actually. So you can kind of incorporate both those ideas into one group, or excuse me, one field, one branch of mathematics. And you get something very interesting. We get these continuous kinds of groups with a notion of continuity. And we also have something called free groups. Those are slightly more complicated. I'm going to get back to you on that. And so I hope you get the picture that there are just so many different subdivisions. I can hardly even scratch the surface of group theory, but I'm just trying to with this first video, and I'm gonna continue. But I just want to describe this is why I can't simply cover all of group theory in a single video, as you might imagine.